Hey guys, back with another video. In this one we will look at the circulation density, which is one of two quantities that we use to better understand vector fields, the other being divergence, which I'll cover in a future video. We use circulation density when we want to figure out two different quantities, and those are the speed that a vector field is spinning an object and the direction that that object is being spun in. Normally, when we have a mathematical quantity that defines both speed and direction, we don't use a scalar, we use a vector. However, circulation density is actually a scalar, and the way that we're able to use a scalar to describe these two quantities is, well, if we said that the circulation density were equal to some value c, then our speed would be denoted by the absolute value of c, and then the direction would be denoted by the sign of c. So if c were greater than 0, then that would mean that our object is being spun in the counterclockwise direction. And if our c were less than 0, it would mean that our object were being spun in the clockwise direction. So if we look at the drawing that I've done on the left-hand side, we have this paddle wheel which has 4 different paddles on opposite sides, and depending on how fast the water is moving and in what direction the water is moving, one of 3 things will occur. Either the paddle wheel will move in the clockwise direction, it will remain still because all of the net forces are canceling out, or it will spin in the counterclockwise direction. So, and the idea of circulation density is that we can actually shrink this paddle wheel down to become infinitesimally small, and then we will understand how the vector field is operating and acting at the infinitesimal level. We'll get a much better understanding of the vector field as a whole because of that. So to get a little bit more rigorous in our definition, let's define first some vector field f of x comma y, and it has 2 components, so m of x comma y, I hat, and then plus n of x comma y j hat. Now what we'll do is we'll draw the first coordinate of the xy plane, and we're going to have a region which we will call A, and the boundaries of A are parallel to either the x-axis or the y-axis. So this is A, and the point here that we will ultimately want to determine the circulation density at is x comma y. And then we've traveled some distance delta x, which is unknown, and then this is x plus delta x comma y, and then likewise we have also traveled some distance delta y, which is also unknown, and this is x, and rather let me rewrite that, so this is x and then y plus delta y. So the idea is, well, if we can imagine that our paddle wheel from earlier is placed on top of this, so the central axis is now pointing out of the page towards us, then the paddles would be like this. And what we can do is we can calculate the circulation around each side, so the bottom, the right hand side, the top side, and the left hand side, and then we can add all those together, and then we will figure out by adding all those together what the circulation around the area A is. And then if we do that, then we can apply a limit to that value to allow A to become sufficiently small, so A would shrink down until it becomes infinitesimally small, and then by applying that limit we will not find the circulation about the area A, but rather the circulation density at the point x comma y. So let's do that. Let's figure out what the circulation about each side is, and then add that together. Well, one more thing that we will draw in here that will help us do that is, let's recall that this is a vector field f of x that is being mapped out on the xy plane. So at each point we will have a vector, and I'm not going to draw all of them, obviously, but I will draw some of them. So there are some of them. So let's first calculate the circulation about the bottom, so the bottom side. Well, that'll be this vector at x comma y, but we only want the x direction of that vector, so we're going to take that vector and we will find the dot product between that vector and this vector, which is, well, it is going to be delta x, which is our magnitude, and then it's in the x direction, which is the I hat direction. Recall our unit vectors j hat and I hat. So this is f of x comma y, and then dotted with delta x I hat. Now our right hand side will be, well, now we're going to use f of this point, so this will be f of x plus delta x comma y, and now we're moving upwards because we will be traveling this way, so we will dot it with the distance we travel, which is delta y, and now not I hat, but rather j hat, because we're moving upwards, or rather in the y direction. Now if we go along the top, so we will find this distance, or rather this circulation. So the top will be, well, let's choose this point as our starting point. So we have some vector that's originating out of this point, and that'll be f of x comma y plus delta y, and then that'll be dotted with, well, delta x is the distance traveled along this side, and then not I hat because we're going in the opposite direction, so we'll want a minus I hat. And lastly, along the left-hand side, we'll have f of, well, now we can use this point again because that is touching that side. So we have f of x comma y, and then this is dotted with delta y because we've traveled that distance downward, and then times our minus j hat because we're moving down. Well, we can actually compute these dot products because we know what f is equal to. So let's write out each one of these, and I'll change colors, it'll be easier to see. So when we take the dot product of this with I, we're going to use the I component, which is m, and then likewise when we do j, we'll use n. So the bottom is m of x comma y, and then delta x, and then our right hand side will be plus n of x plus delta x comma y, and then delta y, and then our top, this will be a minus because we have the negative, and then m of x y plus delta y delta x, and then our left hand side, this will be n, oh, not sure what that did there, n of x comma y, and then delta y. Well, now let's group these together. So we have these m terms. What we'll do is we'll actually take a negative out, and then we will multiply. I'll just write a negative. I don't need the -1. So negative, and then m of x y plus delta y, and then minus m of x comma y. Notice that if we distributed this negative, it would equal what we end up having. And then we can distribute the delta x out. And then what we'll have is we'll say, okay, well, now we can just add, this. So n of x plus delta x comma y, and then minus n of x comma y, and then delta y. Well, if you notice, this looks awfully similar to the definition of a derivative, or in this case, a partial derivative, because m is a function of two independent variables. So if we just take our delta y, and if we divide this by delta y and then multiply by delta y, well, yes, indeed, this right here is the change in y over, or it's rather the change in m over the change in y, and or normally we'll just call that the slope, the change in y over the change in x, but in this case it's the change in m over the change in y. And what that is equal to is, well, that's approximately equal to partial m partial y. And so this is approximately equal to that. And now we have delta x and delta y. And then likewise, right here, if we were to divide this by delta x and then multiply this by delta x so they cancel out, well, this would be the change in n over the change in x, which would be approximately equal to partial n partial y, or partial x. And now we have to multiply by our delta x and our delta y. Well, now what we can do is we could say, okay, well, that's consolidated greatly, and now we can consolidate it a little bit more. So it's approximately equal to, this will be partial n partial x, and then minus partial m partial y, and then our delta x delta y. So what this is equal to is this is approximately equal to the circulation about the area A. So if we were to add all this together, then that would give us the circulation about the area A. But what we want is we want the circulation not around A, but at the point x comma y. So we want our delta x, let me change back to green. We want our delta x to become sufficiently small. So our delta x is really small, and our delta y is really small as well. And then our a will become really small. And we want them to become infinitesimally small until they approach x comma y. So what we will do is we will say, okay, well, we want to find not the circulation about A, but rather we want to find the circulation at the point. So we know that the circulation around or about A, this is approximately equal to delta m, or partial n partial x minus partial m partial y. And now if we divide both sides by delta x and then delta y, well, remember that whenever we talk about density, we always have mass over volume, right? Or we have a certain amount of something divided by the area or the volume that thing is being dissolved in. So here we have our circulation of A over the area of A, which is delta x delta y. So if we take the limit as delta x delta y goes to 0 of our circulation about A over the area of that, then what that will become is this will become not the circulation about A, but rather the circulation density at the point x comma y. And rather than being approximately equal to partial n partial x minus partial n partial y, this will equal exactly partial n partial x minus partial m partial y. So what we've just done is we've found a very concise formula that will enable us to calculate the circulation density, or in other words, how fast the vector field is spinning at a certain point and in what direction it is spinning. And we're able to do that by computing the partial derivative of each component with respect to a certain independent variable, and then applying this operation where we have partial n partial x minus partial n partial y. So in other words, given some sort of vector field that has two components, one m and one n, we are able to find the circulation density of that vector field at any point x comma y. Well, I'll have a couple more videos on this and then how we can build upon this idea and the idea of divergence in order to understand our integral theorems such as Green's theorem and Stokes' theorem, and then the divergence theorem after that. But I hope you found this video helpful and intuitive. Please, if you have any questions, leave a comment below. Please subscribe as well. It will help out the channel greatly. And I will see you in the next video.